Okay. We're ready?
Sí, fine.
Fine, okay. He's fine. So, last lecture of this fantastic event by Raul. He will be telling us about Renyi entropies and QFT and gravity. Please, go ahead.
Thanks, Ale. Okay, today, as the title says again, and as I promised yesterday, I will go to tell you how to compute the holographic Renyi entropy. And also we are going to do a detour in how to compute the holographic entanglement entropy. Because the guiding way of all this thing is know how to do the replica trick in gravity. And if we have time, I will comment the results of Replica Wormholes that people were commenting so much the last 2 years. So let's go. I assume that all of you knows about ADS-CFT, but just I will mention what we are going to use. Let's say that this sentence. Shame on me that I don't have a picture of Maldasen and I put one picture of Renyi yesterday. Shame on me. So ADS-CFT, we have quantum gravity on d plus 2 dimensions, for example, on an ADS spacetime, and this is equal to a CFT in one less dimension, living on flat space, Minkowski space. What is important here is that in the classical limit, we have a general relativity with negative morphical constant in this case, and in the other hand, you have to take the Larsen limit, and this is a strongly interacting system. And this is because this duality is called weak strong duality, because you have weak coupling on the gravity side, let's say, and strong coupling in the field theory. But the thing that we are going to use is this relation between the partition functions of the two theories. It says that the partition function on the gravity side on a manifold M is equivalent to the partition function of the CFT on the boundary of this manifold M. This was studied by these people. The relation is called shaky PW. And more on that, in the classical limit, in the semi-classical limit, we are going to, this can be approximated, as maybe you already know, by the on-shell action in gravity. This is mostly what we need to know about the ADS-CFT. Of course, this is a very simplistic way of introduce ADS-CFT. Now I'm going to tell you how to compute one of the nice things about entanglement entropy is that it is another ingredient in the ADS-CFT dictionary. And I'm going to tell you how to compute it. This is the Ryuta-Kayanagi equation, the Ryuta-Kayanagi proposal that was made in a static configuration, let's say. This is fixed time. In this paper, it was generalized to a dynamical situation. So what they conjecture, and then we are going to prove, is that you have in this green rectangle is the space where the CFT lives, and here is ADS-T plus 2. So suppose you want to compute the entanglement entropy for region A, that is in light blue inside this red thing that I draw. What they teach us is that you have to compute the minimal area of a surface that I call gamma A that ends up on the region A in the field theory, and also that satisfies something called homology. I don't know how to write. Homology condition. This homology condition is means that is written in this. This is like a notation. This homology condition says that exists, I don't know, a region R such that the union of, there exists a region R that is here inside filling this this region. This is the holographic coordinate. I'm doing a picture in the Poincaré coordinates that are this one, where this R is their ADS radius. So this is what they say. This is the equation that you want to know to compute the entanglement entropy in an holographic way. Okay. One easy example is to compute in the vacuum state of a two-dimensional CFT. So we are here in ADS3 CFT2. The entanglement entropy for a segment, for example, that is our favorite. You have a segment between fixed time is constant. And then when you have, what you have to do in ADS3 is to compute the length of the geodesic that goes from here to here. So you can complete the if you want an exercise is to complete the computations. Here I just highlight the central point. This is the action for the geodesics, is the length of the geodesic. Geodesic, I have a very big problem with this one. This is just a redefinition of the constant where it appears the ADS radius and the G Newton. You can compute the equation of motion, so obtain this, put the equations of motion inside this again. And doing this computation, you can obtain this, that is nothing more than, this epsilon is an ultraviolet cutoff that you need because, you know, when you go to the boundary, ADS is divergent, the volume is infinite, so you have to stop in some place. But it's fine because the entanglement entropy in quantum field theory also is ultraviolet divergent. And this is the CFT result that I mentioned yesterday, but quickly because it was at the end. And what you have to use also is this expression. This is the central charge in terms of the Newton constant, the ADS radius. This was computed by Bro and Eno many years ago, noticing that I just know the sentence. I never read the paper, but the asymptotic symmetries of ADS3 forms a Virasoro algebra with this central charge. So using all that, you can see that you can reobtain the CFT result. So now we are going to see how the holographic equation appears. What you have to do to obtain that the minimal area of a surface is the holographic entanglement entropy. Now we have to, I'm just going to draw here what we said yesterday about the replica trick. Remember that what we want, what the replica trick says is that if you have a configuration like this, you have to take n times this sheet to compute trace of rho to the n. So you can have n of this. Okay. Well, let's imagine that they are n. This forms a manifold that I called Vn. And then trace of rho to Vn can be computed. Let's write here as this, where the difficult thing to compute is this quantity, that is the partition function on Vn. So we want to translate this.
Raúl,
Master.
can I ask a question?
Is
there a way?
No, you are muted or cut.
I think it's a problem with the connection. It's very, like, he also looks slowed down.
Ah. I can, but you can listen to me?
No, to Nicolas, can you repeat? You basically, we couldn't hear anything you said. Absolutely.
Yeah, I can hear you neither. Okay. So the question is there a unique way to build this composed manifold when the region to
you are lost
dimensional, two-dimensional, three-dimensional? Again? Okay, it doesn't matter. Okay,
no,
I write it in the chat.
There is a unique way to build. No, you are frozen again, Nico.
Okay, maybe carry on and he will write the question in the chat and we can address it
okay.
when it comes. Okay.
So you have to compute this partition function on this complicated manifold. The thing is how we do this program in Gravity. And then what we are going to suppose is that we have for one sheet that is called V, the manifold is V, one sheet. Suppose you know the ADS dual. You know that the dual of this is another manifold called M. And then what we want to know is which is the dual of this another beast. I will call it Mn. And then the computation of trace of the replica trick is easy because using the GKPW thing, you know that the partition function of the field theory can be written in terms of the gravity action. And from what we saw yesterday, you see that the Renyi entropies are the logarithm of the quotient of this thing is what I wrote here. And using this GKPW, at the end, in Gravity, what you have to compute is this combination of things. You have the manifold, the dual of the manifold Vn and the dual of the manifold M. Here we have to find this manifold. And then one solution that you can think was given by Leukowicz and Maldacena many years ago, like 8 years ago. And what they did? Well, what they think, remember, yesterday I told you, and this is easy to see, you have a set n symmetry here. That is the interchange of replica manifold, replica sheets. What they say is, well, let's try to have a dual gravity solution that also respects this symmetry. And so this is going to be important. This is called replica symmetry. And mostly, I think that 90% of the papers using replica in ADS CFT or in gravity assumes that this replica symmetry is not broken. But I think, and I think there is some few papers, one of them by John Camps, where he studied the case where the replica symmetry is broken. So what they did is to study this manifold M hat. M hat is just the quotient of Mn by the symmetry group. And here they study this because in this manifold they are going to be allowed to do the replica. The manifold, it's easiest. Which is the difference? This is a smooth solution of Einstein equation, smooth. But this cousin is has a how we say a codimension 2 surface where the fixed points of the symmetry set n leaves, these are going to be a conical defect. This is the surface En. If you want in a picture in Mn, what you are going to have is a codimension 2 surface that here I call En, and which are the singular fixed points due to this quotient by the symmetry. So what they did is to translate here on this boundary, you can imagine to have a coordinate system that is centered, if you want, in the codimension 2 surface. For example, let me do another picture. You can have a piece of this En. Then you can have this, a coordinate rod that is the radial direction, and a coordinate tau that goes along the thing. And then in this spacetime, you have, in this manifold, you have a conical deficit that is tau goes to tau plus 2pn. And the deficit angle is 2 pi over n. Okay, all of this is, I mean, as maybe you are now understanding, I'm not going to be in the deep computations that are behind this. I'm just going to highlight how they did it. And all of this is to find an important relation, is that the solution on the manifold Mn is n times the action on the manifold M hat. Then you can use this coordinate system in green that I use here. You can write a metric in that coordinate system. It's going to depend on this, the extrinsic curvature on the codimension 2 surface. You are going to solve the Einstein equations and see that the condition to solve the Einstein equations says that this extrinsic curvature on En has to vanish, and this is going to be the condition that the minimal area constraint of Ryuta-Kayanagi. And the last thing you have to do is to apply this equation that I wrote here. In particular, the people use this refined Renyi entropy that I mentioned yesterday. You see that at the end the relation is to take a derivative of this manifold M hat. And if you do that, you obtain the desired result. Remember that the limit this refined or improved Renyi entropy, also as the original Renyi entropy. This is entanglement entropy. And then you can obtain this relation. There were previous attempts to demonstrate this in a paper by Fursaev. Sí, Ale.
There's a question by Carlos.
Sorry, Raul. I got lost. Sorry, my fault. So while it's very clear how you explain the usual entanglement entropy, it was unclear to me what surface do I use to calculate the Rangamani-Takayanagi, so the Renyi entropies. So what?
No, the same. Here is for any region. Here I'm in this picture. I'm plotting something that has boundaries here, like the segment, for example. But it's any region. I draw this by simplicity. You can have anything like that, and you have this cap.
Okay, but what Rangamani and Takayanagi, what they tell me to do compared to the usual Ryu Takayanagi?
No. What here? No. This Rangamani Takayanagi is just to decide. It's just to. This is a book. It's just to tell you that you can read it here. This derivation that I did. The derivation is more or less explained in this paper of Malda and Leikowitz. What they teach us is how to do the replica trick in holography, how to deal with this M hat and this MN that is difficult.
Okay, good.
I mean, MN, maybe in few slides will be better, but M hat on the boundary is regular. You have a conical defect in the a deficit angle in the bulk, but in the boundary is regular. And then you can write this coordinate system from the boundary to the inside.
I see.
But MN without the hat in the boundary is not regular. MN is you have the thing and you have a coordinate out that is inside the cat. You have a cat here in MN that you don't have it in M hat. This was the goal of them, I mean, to prove this formula using replica tree. Okay. This is not the only way to do the thing. Fursaev, some years before this paper of Leikowitz and Mandasena, did another attempt that had some problems, that now these problems seem that are solved, and this Fursaev approach is useful to compute the Renyi entropies or to describe states that are called fixed area states in gravity. What I was saying, but this is not the unique thing, the unique way to do it. In fact, this MN, at the end you can have many MNs, and you have to find the saddle point of all these MNs, the one that contribute less to the action. And this is why Fursaev find one manifolds and Maldaito and other ones. But at the end, this is more, I mean, you have certain symmetry on the replica manifold. It's natural to try to extend it to the bulk, I think, for IDCFT consideration. It's something natural.
Yeah.
Then they realize how to do it.
Okay. Very good.
But this is just a book. And this derivation is done for any region in the boundary. Just I'm drawing this because simplicity. I don't know if I answered your question.
No. Thank you very much.
So, which is the holographic dual of Renyi entropy? And the answer will be another here. This is a geometrical object for the holographic entanglement entropy, is the area of the minor of a surface, En. Here will be the area of another thing that is a cosmic event that you have to have here. And I will try to explain in two ways how to see that. And as also mentioned yesterday, we are not going to have the holographic dual of Renyi entropy. We are going to have the holographic dual of this improved Renyi entropy. That, by the way, I don't know if this improved Renyi entropy has some quantum information property, some nice quantum information property, let's say. I don't know if this is studied in quantum information. In quantum information, you can study if, I don't know, you have a quantity and you can ask, this is an entanglement monotone or not, or what is measuring. I don't know if this still then has some information in this sense. But this allows to compute, remember that this still then is n squared. I'm going to probably miss the equation, but it's something like that, I guess. Or maybe I wrote it somewhere, don't remember. Well, maybe not. But from one you can obtain no, it's just a one derivative. From one you can obtain the another one. So this was originally proposed in a paper by Xidong in 2016, and this last year was this was again in a static case, and the covariant formulation was done by Rangamani, the same Xidong and more people at the end of last year, and was applied to shady gravity essentially this year in another paper. And here is where, Ale, you can find what you asked me yesterday about the Schwinger-Keldysh path. I think that the Schwinger-Keldysh path, to do in the sense of this computation of replica tricks, has to be explained there. I didn't check.
I see.
But in this first one.
Thanks.
The second one is just application to 2 dimensions of something that they cannot do in more dimensions. So you have to compute the area of the cosmic brane, but it's not any cosmic brane. It's a cosmic brane with this fixed tension that depends on n. And notice that now this is like a coupling. This is like you have an action and you have this will be the Nambu-Goto action. And this is like a coupling. So in this coupling, you can promote n to real numbers, and you are not taking care of this analytic extension. So this n now can have any value that you want. The cosmic brane will backreact the geometry. You will have this deficit angle. This is the same deficit angle we were looking in the Maldacena-Leibowitz case. This is like they were refining the procedure in some papers. When n goes to 1, the back reaction is lost, and you have the computation of the minimal area of a surface that is not a cosmic brane, a geometrical surface. And then what you have to do is to compute the on-shell action, but now the action is the action of the bulk, which is Einstein-Hilbert, plus if you have matter, scalar fields, fermion fields, all that, plus the Nambu-Goto action, or the action of the brane, that is this one. This is the Ricci curvature, is not anymore the ADS constant, Ricci. This is the metric. This is the induced metric, on the worldsheet of the cosmic brane. And so you have to minimize this. One way to see this, that is as Xidong did in the paper, is remember what I said before, you can write the ranges. These ranges you can obtain it by this difference of actions. So you have to find classical solution to this total action. From here it's easy to go in this direction, and then you have to compute the derivative of the action on the bulk on this quotient manifold. So you can do it, and you can use this in the coordinate you want, and you will obtain the correct result, or the result that Sidon proposed. That is this one. Some comment here is that the metric, I mean, you have probably.
Raúl, Carlos has another question.
Please, Carlos.
Raúl, let me ask you this. So, two questions, actually. Can you go a bit more into the transparency 7? That's enough.
7, sí.
This one is perfect. No. Actually, I want the bottom of it here. This is perfect. So, about this cosmic brain, right? So, two questions. The first one is, suppose that in that action of matter, you have something like a B2 field, or things that we have in type 2, right? B fields. Okay. Do they enter into the action of the cosmic brain? Because in the action of a brain, they would enter, right? In the cosmic brain, sí. Would they enter? So is there something like the determinant of G minus B or something like that? That's the first question.
Yes, I don't know the answer. But if I have to guess something, is that it does not enter in the cosmic brain action. Okay. But if someone, maybe I see Pablo is there, or Botas, maybe someone has to add something.
Yes, I can, if you let me.
Oh, Peter, sí, is Peter there?
Okay, no, actually, it's a very nice question we asked ourselves with Raul and with Bota a few years ago, and we wanted to explain this appearance of this cosmic brain raises quite some questions. So there is an alternative way that maybe Raul will briefly touch upon, in which you, instead of putting the brain, like I think in the end, don't need the brain in order to impose a singular a conical defect in the geometry. But actually, I think that the best way to understand this brain is remove the brain and think of that the solution you need has a conical defect in the center. So there is no physical brain. I think that Dong needed the conical singularity and put the brain and forgot about it, and it was very good because he did a great prescription. But I would think of the modern way to understand it is that the geometry you need necessarily needs this conical defect. The geometry that provides the correct saddle that reproduces the CFT results for thermal states is the one. But I would not think of this cosmic break as something physical that would couple with other fields.
See, this is something added by hand, no? You need to obtain such result, and the guy say, okay, if I put a cosmic break with this tension, I will obtain it.
Okay, very good. Can I ask you the second, and if you wish, for matter of time, pass me to the discussion, and that's it. Solving these equations that you are saying here, one needs to solve, will imply solving second order equations with something like delta function singularities, right? Probably.
Sí.
Non-linear partial second order equations, right?
Myself, I never see this solved in many examples, just in the one that Sidon did. That is a very special example of two spheres, and you know a lot of things.
Right.
But at least I never seen another solution, because as you say, it's very complicated. Nobody solved this.
That was the question. Thank you very much, Raul.
Also, I forgot to mention, there is another paper that study Renyi entropies in holography, that is by Myers and many people. But they don't have a dual of the Renyi entropy. It's just they using this analogy with the free energy that I mentioned yesterday, and with thermodynamic object, they compute it in some backgrounds. But it's not that they say this is the dual of this thing is an area or something like that. And there is another way to compute, to demonstrate this equation. There is another way. Instead of computing the action on m hat that we were doing, that in fact is locally the same as Mn away from the conical singularity, we are going now to compute this, and as Carlos said, you can see that the Einstein-Hilbert term, or square root of G times R, on this M hat is the same as a square root of GR on the manifold MN, times these contributions that are due to delta functions placed on the codimensional 2 surface. If someone wants to see the derivation of this, is a paper, as always, by Forzaveos and Solodukin. I don't remember the year, but it's this. So the difference between Einstein-Hilbert action, the difference in the Einstein-Hilbert action between these two manifolds M and M hat is a term that has a delta function, and that indeed you can see is the area of something times the deficit angle that at the end can be written as the Tn that Sidon said. And then I calling Y to this action. This quotient is Y. If you promote the embedding that is here, the embedding of this brain or of this surface, if you promote it to a dynamical thing, you can vary the action with respect to that embedding and see that you are going to obtain a minimal area condition. So you are from all the areas that you can have, the minimal one is what you need. And then from last lecture, we already saw that we can think in a free energy like this quantity trace rho to the n, quotient by 1 over n. And using this, you can minimize the free energy with respect to the fields, where the fields I mentioned is the metric, the embedding, and any quantum field that you have on top of this geometry, using the relation that I showed yesterday, and using that this is 0 because this is on shell, you obtain that the result is the one that I proposed. This is obtained in a different way. There is a third way by this gentleman that Peter mentioned, where you can obtain the same results and you don't need to go away from general relativity, from gravity. You are going to have a gravity. Now what we did is go a bit away. Now we have the action of a brain plus the action of gravity, of Einstein-Hilbert. Well, there is another way that is treating this system with corners and Hayward terms, where you can show that it's not necessity to go away from gravity. Inside gravity, you have also all the information of these Renyi entropies. That is very nice.
Raul, may I ask also? So
yes.
is there any hint that, I mean, in the end, the trick gives a result about the physical theory? No? Is there any interpretation for these auxiliary brains from the physical theory perspective?
You see, if this has some dual in the CFT.
In the original, exactly. In the original theory, can you interpret?
Up to what I think that they are fictitious.
But there has to be something in the physical theory that gives the same.
I mean, in the physical theory, what you have is this singularity in your region.
Yeah.
And in some way, this has to be translated to the gravity thing. I think that this is the way to translate it that she don't find.
I see.
But as you see, as I mentioned, Bota and Peter find another way that does not need this brain. So it's something that is fictitious. This does not have a...
There is no extra ingredient that they need to use from their perspective?
No.
Nothing,
It's just to add a boundary term to the Einstein-Hilbert action. A boundary term that is not given Hawking. It's called Hayward term, that is there when you have corners. And they did a construction where you, adding these terms, you You can prepare the state, compute the density matrix.
Good. And then this is, I mean, is this boundary terms that they find, is there any interpretation from the field theory, from the CFT, as you were saying?
I think that from the field theory, this is a paper by Takashi and I. They are edge modes, something like edge modes.
Edge modes.
Boots or Peter can correct me if they want, but
around what? I mean, what is supporting the edge modes in that case? Is it known?
This I don't know. Peter,
okay, yeah, Peter, perhaps later we can.
Later. Now we are on friends. This is a relaxed talk.
Yeah.
We can talk.
Yeah, maybe the discussion would be better.
Better. How many time I have, Ale?
Basically like 10 minutes, and then 10 more minutes for questions. But yeah.
Okay. And here I go. I'm going to try to explain. All this was had a revival, all this replica tricking holography, because of the apparition of these replica wormholes. That in fact, the idea is a bit simple, but at the end is not so simple. We were doing like you have what we did is up to now is to find the holographic dual for a pile of a replicated manifold, and we find some of them with conical deficit or not, but we find some of them. But now it can happen that it's not like this picture. It can happen that you can have a connection between them, no? When you fill it with gravity, now your geometry is like that. Or if you want, if you have three, your geometry is like, okay, my pictures are very, very bad. Let me see. Let me try once more, but you know, it's a connected geometry in the middle. Between all of them. What happened? Of course, you already had this in the discussion I did, but these are not saddle points of nothing. The saddle point is the one I discussed. The Maldacena solution, or the Sidon, or the Fursadev that I didn't mention. These are not saddles, but in some situations, these are saddles, and these are important. And these are the cases where people study black hole evaporation using quantum extremal surfaces. That I'm going to say, this is a review, you can learn some of this here. But what I'm going to follow is this one. I mean, in these two papers, both of them compute the same thing in different approaches, let's say. Yes, these guys use something called end of the world brains to cut the geometry. Because in this context of black hole evaporation, you will see that we have to cut the geometry and couple the gravity region with a non-gravitational region. To do that, in this paper they use end of the world brains, and in this paper is just, to me, it's more natural, but we will see. I will follow an example of this. What they say is that the proposal to compute the von Neumann entropy has to be modified or redefined, and has this expression. What you have to do is extremize and minimize this quantity that is called generalized entropy, that involves the area term that Takashi and I find, plus a correction. Note that there is 1/g Newton here and g Newton to the 0 in the second part, plus a correction that comes from quantum fields, all the fields you have, living on this surface. That now I'm going to say what thing. This is the von Neumann entropy for the quantum field, for the fields. this X is a surface, codimension 2 surface. And this surface sigma 8 is another surface. This is another surface that is bounded by the quantum extremal surface X that displays X and a cutoff surface that, to my taste, is a bit unnatural. In the example, in the picture that I'm going to draw now, that is the evaporation of a black hole. But in the example that I'm going to do is a bit more natural because this cutoff surface is just the ABS2 boundary. Then in that case, I'm better, let's say. But what happens in this case? In this case, you can have, I'm going to draw the picture that they explain in this review that I told you. This, I'm going to draw the Penrose diagram of the evaporation of a black hole, just to show these surfaces where they are. You will have the horizon. You will have a cutoff surface somewhere. And then, for example, you can have this situation where this is the position of the quantum extremal surface, and this is what I call sigma x. But you can have, sigma. But you can have, there are two diagrams, in some cases, there are two diagrams that compete. One is this, that is connected, but there is another one that is not connected. No, same color. No, too small. So now I will call this sigma r, sigma I, and this is the same x as before. You have this competition. And now what I call sigma x is just the union of sigma r, sigma I. This is what is called the island. And well, from this picture, you can see another things about the entanglement wedge, that this island thing at the end came to say that, look, the entanglement wedge of what is in the field theory, or not in the field theory, what is in the region without gravity, here there is no gravity. The gravity is in this, from the green line to the left, to the right, there is no gravity. And then they say, look, the information of the part that has no gravity is also inside this part that has gravity. So this thing that you were talking about the Hilbert space has to be factorized in Hilbert space inside and outside the horizon, for example, does not hold. This is not true. And of course, what we did before, we proposed the Ryuta-Kayanagi formula and we demonstrated using the replica trick. You can demonstrate also this equation using the replica trick. I will not do that. We will see that if we have time, that this can be obtained in an example, can be re-obtained, but it can be shown that using these replica wormholes, in this case, well, you can obtain this entropy. In this case, when you do the replica trick, there is no wormhole. The replica trick will give you what I was explaining before, a set of n sheets. But in this case that you have an island, you can see that you have a wormhole. A wormhole in this sense, no? You have to find disconnected solutions. The example that I want to do, that was explained in the paper I mentioned before, and also was done in another papers, is the following: one interval, the log one interval in shady gravity, plus CFT at finite temperature. So the setup here is that you have a region with no gravity, another region with gravity, that in this case will be shady gravity, because we are going to be in 2 dimensions. That is the easy thing, but gravity in 2 dimensions is nothing unless you have some trick, and shady gravity has a trick, has this scalar field. And on top of that, we are going to have a CFT2 on both sides. On both sides, there is the same CFT2, and we'll have transparent boundary conditions on the interface between gravity and no gravity. So this is the setup that in this example. So the action on m hat on the quotient space-time, you can check that this is the gravity action. The gravity action is all this stuff that is shady gravity. I will not enter in detail. I think that in the last conference that we did, someone talked about shady gravity, but at the end, this is proportional to the Euler characteristic of sigma 2. This is the dynamical part, but you can integrate out the scalar field, the dilaton field phi, and you will end up with a geometry that satisfies this. The solution to this is AS2. When you evaluate this, you are going to end up just with this equation that is going to be written in a term in something that is called a Schwarzian action, and this is all what remains on your theory. Your theory is a theory of a Schwarzian action for one reparametrization mode. I'm not going to enter in details. And if you want this expression here, in this shady gravity setup, you can see that this is an area. This thing is like the area of the cosmic rain. With some tension, where omega y are the position of the, remember, you have m hat is a quotient, you have fixed point on this zeta n symmetry. These fixed points, I call it W. So you can start with this theory. You can think that this is a new gravity theory. You have this action, and on top of that, you have a CFT action, a CFT thing, and you can replicate this CFT to compute trace of rho to the n. I will not have time to talk about this, probably. This is a technical complication. I will do just the typical picture of this technical computation. Now you have this, you have gravity inside this circle. There is no gravity outside. So you have to paste 2 coordinate systems, the one in flat space and the one in gravity. You have to do it in such a way that the boundary conditions here match. And not only that, you want an holomorphic coordinate transformation, because if your conformal, if you do it in an holomorphic way, you know that the stress energy tensor, that is something that we are going to need, can be written due to conformal symmetry in this way, because you know how it transforms an holomorphic transformation. This is something hard. It's called conformal welding problem. It's not solved in many cases. It's solved in some cases in a numerical way. In this way, it will be exact. I'm not going to enter in detail. But at the end, what you want is a transformation that I call here this coordinate set, that send you from here to here. But here you have two coordinate systems, the flat and the gravity, and here you just have set in a metric like that. Well,
Paulo, can I ask, what
sí.
are the boundary conditions on the interface?
Well, depends for what? For the
To have gravity, to have for the metric and the dilaton, to have gravity inside and no gravity outside.
Well, for the fields is transparent, and for the gravity is the standard ones. I think it's the Dirichlet. Gravity does not, it's IDS2.
Yeah, but if there's gravity that fluctuates, right? Usually you put the boundary close to infinity where it doesn't fluctuate.
Well, but yes, you're right. But you know, this is shady gravity, and you have to, at the end, how to say?
I mean, the question is how you implement this transparency.
Yes, but this is complicated to now.
Okay, we can discuss later.
Sí, because no, I also I don't know the details, the whole details of the computation. But
so,
what I know is that this is, sí, Ale.
Yeah, you kind of have like 5 minutes, including the fact that we're supposed to have 10 minutes of questions. So if you want to have some questions at the end, roughly.
Now, let me see, I can just mention what is there. So we want to prove this. We wanted to prove this for the this entropy, minimizing the generalized entropy. You can do it in you can compute this in two ways. One is using this equation, computing the quantum extremal surface, applying this minimization, this extremization, and you are going to get a result. In the paper, they do it. They did it in many computations, and they apply this formula. I call this quantum extremal surface computation because they use it. But then you want to obtain the same results using the replica trick. And here is where the welding problem is more complicated, because the welding problem in the picture I did here, you just have one copy in this picture. But now you have n copies of this system, and you have to paste it in some smart way. Well, in this case, it's easy. People do it. People find the on-shell action, and this action where this equation was not solved for any n, but you can see, you can take some limits, and in this limit, you can see that you obtain the same result as using the quantum extremal surface condition. Well, the details are in the paper. The paper are very much with a lot of computation, so it is it can be readable. And so, like a summary, at the end, what we learned yesterday is, I mean, my message from all this here, the start yesterday was the replica trick in CFT, in QFT. And when you want gravity, the start will be again how to implement replica trick in gravity. And we saw there is not just one way to do it. You can have many of them, but you have to use the saddle and compute on-shell actions in the end. And, well, no, nothing more. I don't have more time. Thank you, Ale. It's already done.
Okay.